All right, let's finish up with chapter 41. Finish up these last topics. These are looking at, well, half-life and rates of decay. And we had gone over this in the previous lecture. We said this is going to be really important, so, and everything is outlined right here. We've done this in the previous lecture, so I'll do this quickly. If you want a slowed down version, go back to there. But we said as far as decay rates, what we're trying to come up with are formulas that tell us if I start with some number of radioactive nuclei, as a function of time, how many of those will be left. So what we did was define a decay rate, or a rate of decay rather, sorry, a rate of decay that's proportional to the number of radioactive nuclei that are present. And we introduced the idea of a decay constant with that. We carried out an integration and came up with this formula. So it says that the number we're going to have is decaying exponentially. That says that if I look at the number over a period of time, we're going to have this exponential drop-off, and it's going to asymptotically approach zero. Now, this might lead to one of those paradoxes, one of those mathematical paradoxes, and go, well, wait, then there's always some of the sample left, right? And you go, no, there's going to be some point where that last final nucleus decays. There's going to be some point where this function drops well below the number 1, and you go, at that point, it's unlikely that anything is left. In fact, the actual, this is just a theoretical curve. Statistically, what's happening is every time there's a decay, we start out with n naught, right? Let's say we start off with 100 radioactive nuclei, but sometime it drops to 99, then it drops to 98, 97, 96. So that would make it a series of step functions, right? There's a step down, another step down, another step down. Well, at some point, that last step, that last radioactive nuclei does decay. Now, statistically, we can't really predict exactly when, so this curve becomes a theory curve as to our best guess as to how the numbers will drop off with time. All right, and that came from carrying out this integration. Now, between there and here, what I've done is I've switched out of decay constant, and I am now using the lifetime, which is the inverse, and my justification for that was that this is kind of the standard way we represent exponential functions. The lifetime actually has units of time, and the lifetime we have here corresponds to the time constants that we used back in Physics 4b. So I'm trying to stick with that convention and use tau as a scaling factor for the exponential drop-off. Now, there's another version of this called the half-life, which is related to, well, the half-life is the ln of 2 times the lifetime. And it's actually the half-life that shows up in Appendix F. We'll be looking at a number of examples, so we'll talk about that. Now, the second function that we introduced, we said rather than just counting how many nuclei are in our sample, the other thing we could do is keep track as a function of time at what rate are decays taking place. And the decays are going to occur at a slower and slower rate. As the sample size comes down, the decay rates are going to drop off proportionally. So we said this formula keeping track of the numbers, this formula keeping track of the rate, and a warning here, let's see, the textbook, instead of defining big R, which I think is a sensible thing to do, the book continues using dn dt. And I always feel like that's too much notation to carry around, so my recommendation would be go ahead and use the big R that we've defined here in lecture for your problems. I hope that makes it easier. You definitely want to understand what R means, but that's a lot of notation to carry around. So we have this graph for decay rate. The formulas connecting R's and N's with the lifetime are given there, and we said that's kind of the whole picture. If you understand these graphs and these formulas and how they're connected, we should be able to get through all the examples that get thrown at us. So let's throw one now and see how this is all going to work. A couple more steps, I guess, that we can take a look at. If we're working in terms of half-life, let's say that we start off with N naught and then 1 half-life. Now the numbers they're showing here, this is for carbon-14, so it's not just some random material they've come up with. Carbon-14 has a half-life of 5,730 years, and so that is the example they're looking at. So here is 1 half-life that's passed. Here are 2 half-lives, and here's 3 half-lives. And the idea is, if we're thinking in terms of half-lives, then each time 5,730 years goes by, we'll have 1/2 the sample size. And then it drops to a 4th, and then it drops to an 8th, and then it drops to a 16th, and then it drops to a 32nd. So half-lives, it's kind of easy to keep track of those factors of 2. Now what it's also saying is, for the sample size that we have right there, if we carry out the calculations, a sample of carbon-14s where we have 1 times 10 to the 22nd. Now that's a small, what is that? It's less than a mole. It's like 1/10 of a mole, less than 1/10 of a mole, 1/60th of a mole of sample size. That's going to be decaying at 4 times 10 to the 10 decays per second. So here is the R graph. They haven't got the formula here, but this is the R, or decays per second graph. Oh, here it is, dN dt right there. And then after a half-life passes, we'll be down to 2. They didn't get that dashed line to match. In fact, they didn't get the green line to match up either. All of that got shifted somehow when they printed this out. But the same thing's going to be happening in decay rate, down to a 1/2, a 4th, and an 1/8. So that's how these decays play out. Now, going back to the graph that we had explained here, let's look at the difference. If I'm looking at half-life, right? Half-life's keeping track of when the numbers and the decay rates have dropped down to 1/2, whereas lifetimes, working in base E, are keeping track of how much time until it's dropped to 37%. Remember our old friend, 37%, that's 1 over E. Instead of 1 over 2, this is 1 over E. And so after a lifetime has passed, we'll be down to 37%. 2 lifetimes, 14%. 3 lifetimes, 5%. So we've looked at those examples before. Here's just a reminder of what the formulas look like relating half-lives with decay constants. Now, we're mostly going to be doing this the other way around because we're going to be looking stuff up in Appendix F. We're going to be looking up numbers and taking the half-life numbers from Appendix F and converting those into primarily into lifetimes or decay constants, either one. So here's our first example, and it actually is carbon-14 that they're taking a look at here. So it says, here is a sample problem for measuring radioactivity. Carbon-14 has a half-life of 5,730 years. If we start off, this is the same graph as before, if we start off with a sample size of 1.00, 10 to the 22, carbon-14 nuclei, what is the activity of that sample? Now, we have a, first thing we should point out, this is a very concentrated sample of carbon-14. We have a very, very large number of carbon-14s, and apparently the sample has been purified. So somehow we've used a mass spectrometer or something. We've actually sorted out all of the carbon-14s and grouped them together. Now, the carbon-14 has a long enough half-life, we could actually do that. You know, if it was a really short half-life, we go, that would be a hard thing to do, is sort out a large sample of radioactive nuclei if they're decaying very rapidly away. But 5,730 years, that's going to give us some time to prepare this sample of radioactive carbon-14. So here we go. Let's see what that example looks like. So first of all, they wanted to know what's the decay rate. So here we go. Decay rate, we said back when we were deriving these equations, I can always calculate a decay rate by taking the current number and dividing through by the lifetime. Now, let's come over here. What is the lifetime given by? Because when I look up in Appendix F, not the periodic table, when I look up in Appendix F the data for the carbon-14 isotope of carbon, it tells me that there's a half-life, 5,730 years. Now the formula for us is to take that half-life and divide through by the ln of 2. And we looked at that equation before in some variation also. So I'm taking the value that I picked up in Appendix F and converting it into a lifetime, because that's my personal preference. I'm going to do all my calculations in terms of that. Now I'm double checking, and I'm double checking by noticing that my lifetime is always going to be longer than the half-life by, 30, 40% or something. And that's what I'm seeing. I'm going from 5,730 years for the sample to drop to half, but it's going to take 8,267 years for the sample to drop down to 37%. And so this is that value in years. Now, if I'm calculating a decay rate, I probably don't want the number in decays per year. You got to start thinking for homework problems and for midterm problems and for the final exam. Make sure that you always report your decay rates per second. If you say decays per year or decays per billion years, that's hard to think of what that would look like. I want to know in the next second, how many decays am I expecting? So I'm going to take those years and convert them into seconds, and I did that right here. And just a quick reminder, a year is 31.56 something million seconds. So very roughly, it's like 30 million seconds in a year. Okay, and that's why they fly by so fast, right? Whoa, that year went by. That was, those 30 million seconds, they went by pretty fast. And you guys know how to get that number. And I always start with an average year is 365.25 years. You got to average over the leap years, right? So anyway, that's my number of years. This is what the lifetime looks like in terms of seconds. So I've got that. Now in the problem, they already told us our sample size. They said the sample was 1.00. That's 3 sig figs of precision, 10 to the 22nd. If I divide that through now by the lifetime that I just calculated, it says, oh my gosh, that's a huge number. So I ended up with a decay rate of these carbon-14s right now, every second, is I'm getting 3.83 10 to the 10th. So that's 38 billion decays per second happening in this sample. And what that reminds us is atoms are really tiny. Let's think about what's going on here. I'm getting these 38 billion decays per second, how long is that going to go on for? And the half-life of this is thousands of years. It's going to take thousands and thousands and thousands of years to see a significant drop-off in that decay rate. So you're going to continue to get billions and billions of decays every second for thousands and thousands of years into the future. This stuff is still going to be around. There's going to be a significant amount still around, 40, 50,000 years from now. There's still going to be measurable amounts of this, and it's going to be decaying. That's just amazing to me that you can have these extraordinary decay rates, and they're going to go on for thousands of years. And that raises an important question, at least it made me a little curious. Just how big is this sample of radioactive carbon-14? Now, it's a pure sample. Every atom in there is radioactive. How large of a sample is that? What would the mass be? So I took the 1.00, 10 to the 22nd, and I multiplied that by the molar mass. Now, the molar mass of any isotope is just its mass number. So the molar mass for carbon-14 would be 14 grams per Avogadro's number. And what I ended up with was, again, I'm thinking at least, this is kind of an extraordinary number. The actual sample size that I'm looking at is 0.232 grams. I have 230 milligrams of this carbon-14. Now that's observable, right? If this was a powder of carbon, and it could be graphite, right? It's carbon, it could be a diamond. So I could take all these carbon-14s, that would be really cool, right? Take a bunch of carbon-14s, form a diamond out of all the carbon-14s, and then over thousands of years, one by one, those carbon-14s decay into nitrogen-14. One by one, the individual carbon-14s are gone. Or it could be graphite. So it's going to have the same chemical properties as carbon-12 does. Anything you can make out of carbon-12, you can make out of carbon-14, but be careful. Step back away from the carbon-14. Maybe get something mechanical to do that remotely. All right, so a couple hundred milligrams, this little tiny sample of some carbon-14 graphite powder, and that's going to be decaying at billions of decays every second for the foreseeable future, right? Thousands, tens of thousands of years into the future, you're still going to have significant decay rates. Atoms are really tiny. There's a lot of atoms. That gives you an idea also of just how large numbers like 10 to the 22 really are. It's easy for us to get a little complacent with scientific notation, kind of thinking, 10 to the 22, 10 to the 44, 10 to the... What are these numbers really? They're enormous numbers. All right, that's our carbon-14 example that we're looking at here. Here's an interesting question, conceptual question. One might think that a shorter half-life material is safer than a longer half-life material because it won't last as long. What do you think? Let's go back to this example with the carbon-14. With this sample, maybe this is the best slide to work from. Would you rather see all of this carbon-14 decay quickly, or would you rather have it, or would you rather flatten the curve to refer to a current popular expression? And having a longer lifetime is flattening the curve. So what it's saying is that I'm going to have this around for a lot longer, but what that's going to do is it's going to keep the decay rate much lower. Let's get back to a formula that shows that a little better. Maybe here. So what it's saying is, do you want to have a really high decay rate over a short period? Eventually they've all got to decay. So do you want them to decay over a shorter period of time, or do you want to spread those decays out so that the decay rate itself is much lower? I've got a certain number that I want to decay. I'm thinking, if I'm going to be exposed to this stuff, I want that to decay at a really, really slow rate. Okay, so these short half-life materials release all of their energy over a short period of time. So in safety terms, that's kind of what we're looking at. Now, if you're looking at material coming out from a nuclear power plant, right? So a nuclear power plant is going to be generating a lot of radioactive materials. Some of those are very short-lived. Some of them have very, very long lifetimes. So the short decay, the ones that decay very rapidly, actually can add to the thermal energy being generated in a power plant. You can actually be getting some energy from those early radioactive decay products. And then we are left, so this is the other side, this is the flip side of this. What's the concern about having something with a long half-life? And you go, well, it's not as intensely radioactive, but it's going to be with us for a long time. So if you have materials, like carbon-14, that have lifetimes of thousands and thousands of years coming out of your power plant, you're not getting rid of those anytime soon. Those are going to be around. You're going to have to find some way to manage them. They're lower level than the short half-life materials, but those are the ones for a power plant. Those are the ones of bigger concern. So if you had a power plant, you'd rather have something produced that has all the short half-lives, build a lot of protective concrete barriers to protect yourself from those materials, and just have them decay quickly. But if you're going to be exposed to something, you probably want to spread out the decays. All right, here's another example. So we took a look at carbon-14 and its decay and sample size. These are all really good examples too. So just letting you guys know, these are favorite examples that I like to put into midterms or final exams or whatever. Not necessarily these in particular, but sort of problems that ask the same sort of questions. So there's a number of questions going on here. I've got this radioactive nitrogen-13. So remember nitrogen-14, boy, that's a really stable nucleus. Nitrogen-13, not so much. It actually decays into carbon-13. We'll see that. So it says this, it says in a laboratory, we have 1.49 micrograms of pure nitrogen-13. So this time, we've created a sample of nitrogen-13, and it's pure. Every one of those nuclei in there is nitrogen-13, and it's going to radioactively decay. We have a pretty small sample size here, 1.49 micrograms. So now we are really getting down to the size where, the point where it'd be, that's a small sample size. But this time the half-life is 10 minutes. Now, this creates some more problems as far as, how do we collect all these nitrogen-13s when they're decaying in a short period of time? How do I get them measured? Maybe any measuring technique I'm going to have is going to take some time. So this becomes more problematic in verifying just how much you have, because it's a quickly moving target. These are going to be decaying right away. In medical applications, when we use radioactive isotopes, which we do for many different things, we want a half-life long enough that we can prepare a measurable dose for patients. So in iodine, or I'm sorry, in thyroid gland conditions where patients, maybe they're hyperthyroid, their thyroid gland is producing too much thyroxine, that thyroxine makes the metabolic rate of the cells too high. One of the procedures that's done for that is to give the patient radioactive iodine. iodine given to a patient is taken up exclusively by the thyroid gland. So that means that it's targeted just to that one part of the body. And we want a high enough radiation dose to the thyroid to kill every cell that's there, or at least have it stop producing the abundance of thyroxine. In that case, you're going to be trying to come up with something that has a half-life of maybe a few days. You want to be able to give this to the patient, a measurable quantity, but you don't want the decays to go on for weeks or months. You want most of the decays happening at a measurable rate. Now what that says is if you're going to give a radioactive sample of something like this to a patient, you have to not just measure the dose accurately, you have to calculate at what time the patient needs to take that dose. Because if the patient shows up a few hours late for their treatment, then there's always the possibility that part of the sample that you intended to give to the patient for their thyroid has already decayed. So again, you have to get the right sample size to start with, and then time carefully, reasonably carefully, when the patient actually is going to take that dose in. So let's take a look at this problem. This has got a lot of nice parts to it. It's asking how many nuclei are present initially, so we get to go in and calculate sample size on this. What is the activity? At what rate is this sample decaying? What would happen to the activity after an hour? Now, when we were looking at carbon-14 in the previous example, that had a half-life of 5,730 years. What happens to the sample size in an hour? Not much, right? If it's got a lifetime of 5,007, or a half-life of 5,730 years, after an hour goes by, that's not going to make much difference in how much is there. But this sample is different. Its half-life is really short. So if the half-life is only 10 minutes, once an hour's gone by, how much is going to be left? And we can already kind of estimate this, or we can actually calculate it. If we have a 600-second half-life, 10 minutes, once an hour has gone by, that is 6 half-lives. That's 1/2 times 1/2 times 1/2 times 1/2 times 1/2 times 1/2, which is 1/64. So we can already calculate this one. After an hour's gone by, we're going to have 1/64 of the original sample remaining. That's it. That's how much will be gone. Will be remaining. And then, this is kind of interesting too. How much time do we have to wait until the decay rate has gone down to 1? What they didn't do here is they didn't ask how long do we have to wait until we have 1 left. That would be an interesting one to check. I didn't run those numbers, but we could think about how that number would be done. All right, here we go. So here is our written up solution to that particular example. And what we're looking at is nitrogen-13 activity. It says that we have a sample that has a mass, 1.49 micrograms. Along with that, we have a half-life that's 10 minutes or 600 seconds. So let's do this first. What they wanted us to do was come up with how many are we actually starting with. And in this example, they've given us the mass, and that's enough information. From the mass, we can figure out how many radioactive nuclei we have in our sample. So 1.49 micrograms. Now for nitrogen-13, we're going to have 13 grams per mole, and a mole is 6.022 times 10 to the 23rd, and carrying out that calculation, now that's micro, that's 10 to the minus 6. I ended up with 6.90, 10 to the 16. So, a tiny, tiny fraction of a mole this time. So it's a smaller sample size than we've looked at in the previous examples, but that is the N naught. Now, how would we determine at what rate, at least initially, these are decaying? And for that, we can calculate R naught by taking the N naught that we've already calculated and dividing through by the lifetime. So the lifetime calculation is here. So the lifetime we can get by taking the half-life, that's what was given in the problem, or maybe that's something we looked up in Appendix F. So if that information is given to us in a problem, then I can take that 600 seconds, divide through by the ln of 2, and that gives me 866 seconds, and I do a quick mental double check and go, yeah, that seems like it's extended by an additional 40% or something. That's how the lifetime is related to the half-life. All right, so with this in place, I can put in the N naught value and then divide that by the lifetime. And when I measure that, I get 7.97 10 to the 13 decays per second. So that's happening pretty fast. I'm still getting 80 trillion decays per second. So the sample size was only, 7 times 10 to the 16, and I'm seeing 8 times 10 to the 13 essentially decaying in that first second. Now, since it has such a short half-life, not only are the numbers going to drop off pretty rapidly, the decay rates also will drop off pretty rapidly. So let's see what happens. After, now in part C, they are looking at 1 hour. So this is the after 1 hour question. And after 1 hour has taken place, I can put 3,600 seconds right here and divide that through by the lifetime. I can take each of those values, and that's what I've set up here. So what this is telling us, when I carried out that exponential calculation, this is going to become R naught times 0.01565, and surprisingly enough, that number right there works out to be 1/64th. And that's what we had anticipated. We had talked about that. We had said, oh, you know what's going to happen here is the one hour is exactly equal to 6 half-lives, and that means that 1/2 times 1/2 times 1/2, I got to take 6 of those, and that will leave me with 1/64th of the original sample, and it will also leave me at 1/64th of the decay rate. Finally, in this last part of the problem, it says that at what point will the decay rate drop down so that it's decaying just 1 decay per second. Now this was like 1 trillion decays per second, down from 80 trillion decays per second. For this calculation, I'm going to come back to this, but I'm going to solve for time. This is asking how much time is it going to take, so I'm going to use the same equation, the equation from here, but again, I'm going to solve this equation for time. So what I've got then is e to the t over tau is equal to r naught over r. Now the minus sign is gone. Another trick for getting rid of minus signs is I wrote this as r naught over r. I didn't write it as r over r naught, I wrote it as r naught over r. And that says that I'm putting the r naught on top and the r down below. So I'm starting off at that 7.97 10 to the 13th, and I'm asking how much time until that will have dropped down to just 1 decay per second. If I carry out that calculation in terms of t, that's what it looks like. So the t is equal to the lifetime times the ln of that ratio. And when I carried out the ln of that ratio, that worked out to be about 32. So I'm going to have to wait 32 lifetimes, not half-lives, but lifetimes. 32 lifetimes will be enough to bring us all the way down. That's going to be 19,200 seconds, which I then converted into hours. So it's saying, oh, if I've got something with this really short half-life, in a matter of hours, it's going to be down to just 1 decay per second. And it will continue to drop off pretty quickly. A few more half-lives, and we will have brought that down to not that many more hours until the sample is essentially gone. All right. Questions on any of that? Okay, so again, a good example problem of keeping track of numbers and decay rates at different intervals of time. All right, now when we look at naturally occurring radioactive materials, we had said this. Let's see, we're looking at what's called a decay series. Now, what they've got on the horizontal axis here is they've got these different elements listed. So here is lead, bismuth, polonium, astatine. So it's all of these radioactive materials that occur naturally. Now, what happens is this. In the periodic table, lead, element number 82, and bismuth, element number 83, those are the last two elements in the periodic table that have any stable isotopes at all. Everything past lead and bismuth, starting with polonium, every element, all the isotopes of that element, they're all radioactive. There is nothing that is a stable isotope beyond that point. Now, you might think, well, where are these all coming from then? If everything beyond lead is radioactive, why is there any around at all? Now, earlier we had mentioned that if we look, well, a little bit of astrophysics we can throw in here. If you go back billions and billions of years, if you go back to the early universe, all you really had were protons and electrons. And through generations of stars from those early hydrogen samples, from those hydrogen, clouds of hydrogen through the universe, stars formed through gravitational collapse, nuclear fusion reactions set in, and stars started out the process of generating heavier elements. So in astrophysics, all of the elements of the periodic table are categorized in three categories. The three categories of elements in astrophysics are, well, category one is called hydrogen. Hydrogen by itself makes up about 75% of the material that's out there. The second category is helium, because helium makes up most of the rest. And then the remaining few percent are the heavy elements. So in astrophysics terms, everything starts out as hydrogen. A fair amount was converted to helium in the very early stages during what we consider to be sort of the first 3 minutes of the universe under extreme conditions. But since then, only stars have been able to generate all of the rest of the elements of the periodic table. So when you ask, well, where did all these heavy elements come from? They came from nucleosynthesis inside stars, and we'll see that in more detail in chapter 44 at the end of the semester. Now, the solar system that we live in formed about 4.5 billion years ago, And it formed from leftover debris from earlier generations of heavy stars that generated heavy elements. Now, again, you might say, well, sure, the stars generated all these heavy elements. Why are they still around? Shouldn't they have decayed by now? And there's a few of these elements out there that are kind of the last holdouts. And one of the most prominent ones, is uranium-238. Uranium-238 has a half-life of 4.5 billion years. If it were not for the long half-life of uranium-238 and uranium-235, a couple of these long half-life isotopes of uranium, most of these other radioactive materials would not be here. So if you look at the radioactive, if you look at the lifetimes of some of these other materials, 75,000 years, 1,600 years, 3.8 days, 3.1 minutes, or 0.04 seconds. Some of these have much, much shorter half-lives. But these isotopes of uranium have these long half-lives in the billions of years. And so that becomes a steady source for generation of all of these different isotopes. So again, what we have is polonium, astatine, radon, francium, radon, actinide, thorium, protactinium, and uranium. Those are naturally occurring radioactive materials. And all of these isotopes are continually being regenerated by decays of uranium-238. So let's think what happens here. A uranium-238 undergoes alpha decay and turns into thorium-234. Well, it took on average 4.5 billion years for that reaction to occur. For the thorium, that's going to decay on average in 24 days. So we waited a long time for that, and then the thorium decays almost immediately. And then the thorium becomes protactinium, and that decays within a few hours, and that turns into uranium-234. The uranium-234 is around for, hundreds of thousands of years, but that's nowhere close to this billions of years. So every time the uranium-238 decays, it sets off this decay series. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It takes 11 decays until it turns into an isotope of lead. And so it's kind of like the starting gate, right? We're waiting for a uranium-238 to decay, and whenever it does, then it's followed over the next hundreds of thousands of years by 11 subsequent decays that happen in much shorter amounts of time. And you can see that there's actually some alternate paths here. Some isotopes have more than one way of undergoing decay. And that's what we're seeing from the diagrams here, is we're seeing those. So it's kind of interesting to look at these decay series. Now, what we have on the vertical axis is we have the mass numbers. So along the horizontal axis is element number, atomic number, and what we have on the vertical axis is mass number. Now these are written in at 4 at a time. These are written 1 at a time. And that says that whenever an alpha decay occurs, an alpha decay would reduce the number of protons by 2, and it would reduce the mass number by 4. So anywhere on this chart, if I pick an isotope of a particular element, if it alpha decays, that's going to take me to the left by 2, and it's going to drop me on the vertical axis by 4. And so all of the red lines are alpha decays, and that's what they are doing. All of those red lines have that same shape to them. They drop by 4, and they move to the left by 2. Now the beta decays that are happening here are all beta minus. And that's because when we get to the end of the periodic table, primarily there's 2 effects going on. The first effect is everything's too big. If you get too many protons and neutrons packed together, it's just not stable. And so the alpha decays are just reducing the size of things pretty quickly. A series of alpha decays will bring down the number of protons and neutrons. But what happens is, when you keep doing alpha decays, you've got this extra surplus of neutrons, and as you do a series of alpha decays, that neutron to proton ratio actually keeps getting higher. And so every once in a while, after you've done a series of alpha decays, you need a few beta decays because you're building up too many neutrons. You need to take some of those extra neutrons and turn them into protons to make things more stable. So we can see that alpha decays, and then we have a couple of beta decays to get rid of some excess neutrons, and then we go through a series of alpha decays. We get much, much shorter, but we do a couple of beta decays to get rid of the excess neutrons, and so it's kind of a back and forth. So a beta decay, actually by getting rid of a neutron, it turns it into a proton, and that means that we take a step forward in the periodic table. We actually move to an element farther into the periodic table, but its isotope remains the same mass. So the beta decays, one fewer proton, or one additional proton, but the mass number doesn't change. So those are the only two options. I've got red lines that go like this, or green lines that go like that. And it's going to be some combination of those that show up in each of these decay series. Okay, and you can see at the end of this what's happening. All of these decay series end up with some isotope, one of the stable isotopes of lead, or as one of the stable isotopes of bismuth. Those are kind of the endpoints for us. These are all ending in lead-82. If we looked at the decay series for uranium-235, that would end up with some of the isotopes of bismuth. So kind of those holdouts. I always wonder how our world would be different if uranium-235 and uranium-238 had much shorter half-lives, maybe a few thousand years instead of a few billion years. And the first thing that I think comes to mind is there would be no nuclear weapons, right? We would have no way to build nuclear weapons. We would not have materials that would undergo fission. Seems like a plus. We could give up the nuclear power plants if at the same time the ability to build nuclear weapons would go away. So unfortunately, I feel these isotopes do have these long half-lives, and we're kind of stuck with this material, and we have to learn to work with it responsibly. All right, so here's the decay chain. They're talking about this decay chain and which of these would have the highest rate. Which of these intermediate materials would have the highest rate of decay? And I think the answer to this then would be what's going to happen with these materials, keeping an eye on the clock here, with these materials, what's going to happen is every time uranium-238 decays, what's going to happen is we're going to get one decay each for all of the intermediate numbers. So even though they have short half-lives, all of these short-lived radioactive materials have to wait for a uranium-238 to decay to set off the whole decay series. So in a sample, they should have kind of comparable decay rates. They should all have similar decay rates because a lot of these materials will exist at really low concentrations inside there. Okay, so the rate should be pretty comparable. All right, we're down to our last topic for the chapter. And this is using carbon-14 to carry out radioactive dating. So the idea here is this, and we've already talked about this a bit. So I'm going to skip these two slides. What they're pointing out is that there's this new source of carbon-14 being regenerated in the atmosphere constantly, And so it turns out that the carbon dioxide in the atmosphere, of those carbons, 1.3 carbon-14s for every trillion carbons. Now we've looked at some examples with carbon decay already, carbon-14, and so we've looked at the half-life, 5,730 years, we've looked at the lifetime in years, and we've looked at the lifetime in seconds. So let's do this calculation. Let's say that we take a kilogram of carbon from some living organism that's actively metabolizing, say, you, right? So you probably have several kilograms of carbon within you, and 1.3 of those carbon-14, 1.3 out of every trillion carbons is carbon-14. So the first thing we could say is, okay, let's take this 1 kilogram sample of just carbon. That's 1,000 grams of carbon. Carbon has a molar mass of 12 grams per mole. That would say that the total number of carbon atoms in my 1,000 gram sample is 5.02 10 to the 25th. Now, how many of those are carbon-14? And so I can start off with this 5.02 10 to the 25th, and I can use that ratio. So 1.3 for every trillion, and it says, oh, for every kilogram of carbon in a living organism, there are 65 trillion carbon-14s, and that includes each of us. And so that would be the number. At what rate is our indigenous carbon-14 decaying per kilogram of carbon? And that would be the number divided by the lifetime, and we've calculated the lifetime in previous examples. And what that's telling us is for every 1,000 grams of carbon inside of us, 250 decays per second. Now I'm guessing, you know, I'm like 70 kilograms or something, and or more than that probably, 70, 75. And so I've got to be, you know, 70% water or something. But of the remaining 30%, a good portion of that is carbon, maybe half of it. So I've got to have several kilograms. So that would say, you know, a typical person has a decay rate from carbon-14 well over 1,000 decays per second. So that would encourage social distancing, right? If everybody around you is radioactive, and they're decaying at rates of thousands of decays a second. Now let's think on the other side. When we did those calculations with carbon-14, the decays were not especially energetic, and half the energy went into a neutrino. That's not a concern. And they're beta decays. So what would happen then is when a carbon decays, it's already built into us. It's going to do local damage. It's going to break up some chemical bonds. And we kind of have to count on those mechanisms within our cells to go through and check for errors that may have come up in our DNA, or keep recycling our proteins and other materials inside of us to make sure that we're made out of things that have been recently built, to try and take into account this, you know, 1,000 decays per second of carbon-14 taking place inside of us. Other people are probably going to be safe from that. None of the particles coming out would be energetic enough to leave us and go to another person. So this is totally something we'd have to be more concerned about within our own physical well-being. From our own decays, we have to take responsibility for our own decays. All right, we can actually use this carbon-14 decay method to be able to carry out measurements of how old different samples are. So let's say you're an archaeologist, you're analyzing a site where there was a human civilization or a village, let's say, going on, and you find that there's some animal bones, and maybe those animal bones were used by the people in the village, you could use a sample of carbon from those bones and find out what the activity rate is of the carbon and determine how old those bones are. So again, as long as an organism is actively metabolizing, they're taking in new samples of carbon-14 and they maintain that level of 1.3 parts per trillion. But when you die, you're not taking in new sources of carbon-14. And so the decay rates and the number of carbon-14 drops off with time. So let's say that we have this animal bone. This was the problem posed on the slide before. It says we took an animal bone, and from that animal bone we ran some chemical techniques, and we sorted out 200 grams of carbon, so pure carbon from the bone. Now, that would say that 200 grams of carbon would mean 1.30, 10 to the 13 carbon-14s originally were present in that sample. Now that says at the time that the animal died, this particular 200-gram sample would have been decaying at a rate of about 50 decays per second. So that, again, that 200-gram sample would have had this many carbon-14s. We put in our carbon-14 ratio. We put in our lifetime and 50. Now what they said was, in the problem, they said that the archaeologists measured this and it was only decaying at a rate of 16 decays per second. So how could we determine the age of this sample? And so what we're going to do is come back to our formula showing how decays are going to drop off with time. So I can look at this expression, and for R0, when the organism first died, stopped actively metabolizing, taking in new sources of carbon, the decay rate would have been 50 decays per second, but now it's only 16. I plug those in, and that says that 1.14 lifetimes have gone by. So that's the number of lifetimes, and then that would correspond to 9,420 years of time since that animal stopped actively metabolizing. So this carbon-14 techniques, that's pretty handy. Anything that has organic material in it, which was once actively metabolizing and it is no longer, we can come up with these determinations of how long ago that's been. Now we only have a 5,000 or 6,000 year half-life, so if the sample sizes get too small, if too much time has gone by, the decay rates will have dropped down to where it's more difficult to do these calculations. Now on the other hand, something like uranium-238 has this really long half-life to it. We could use uranium-238 to determine how old rocks are. So some of the oldest rocks have been dated using uranium-238 crystals, and you can actually look inside, and we looked at that decay series. You can see all these different isotopes of these different materials present, and by looking and analyzing how much uranium is there, how much lead has been produced, we can figure out how old those rocks are. And again, we date those back as being billions of years. For detection of radiation, we have different kinds of devices. We have Geiger counters. We're going to go through this pretty quickly. I'm not as interested in looking at these in detail, but you should be aware there are these Geiger counters. High energy particles come through. They set off a signal based on high voltage setup, and we can count the number of radioactive particles coming through. Scintillators are another way that radiation can be detected. Here is a high energy particle going through a detection chamber. Here's another detection chamber, and that's it. That pretty much wraps up chapter 41. So here is a summary of the topics that we've looked at. I'm thinking we're kind of running short on time, and we've looked at this in some pretty good details, so I think we're good. We'll stop there with chapter 41.